Okay, so uh, welcome to the second of two videos regarding the area problem. All right. So in the last video, we went through and talked about the various aspects of summations and finding the limits of summations. And although it can be complex algebraically, really the only tool that you need to do that is the tools of algebra. All right, and just keep track of your n's and your other variables. It brings us, however, to the main point of section 12.5, which is all about what we call the area problem. Now, when Sir Isaac Newton decided to when he invented the calculus, the reason that he did this was to solve problems of this very sort, because he knew that the area under a curve was equal to the to whatever variable he was trying to calculate at the time. In other words, whatever was on the y-axis and whatever was on the x-axis together in some kind of geometric shape would give him a value. Force equals mass times acceleration. If you took physics in high school, is one example. The moral of the story is that you now have all of the tools needed to solve the second basic problem of calculus, which is the area problem. And the problem here is simply to find, that should say find, there should be a D there, the area of the region R bounded by the graph of a non-negative continuous function. So here's a non-negative continuous function. Whoops, I'm off the line here. F, the x-axis, and then the vertical lines x equals a and x equals b. All right. So essentially, I'm looking for the area that's bordered by these four lines and curves. Now, if this R was a perfect square or a perfect rectangle, calculating the area of it would be very, very easy, right? We just length times width, bam, we're done, okay? Even if it was a triangle or a circle, we have geometric formulas for area of all of those kinds of shapes. However, because this is not a geometric shape, or at least not a regular geometric shape, we have to use the calculus, all right? And the way that we do that is to find the limit of a summation. So the question is, what in the name of all that is holy are we actually summing up? Well, what we do here is we actually take this geometric shape and we break it into a bunch of, tiny little rectangles all the way through. I'm not going to draw them all right? And because we can calculate the area of a rectangle, we now just sum the areas of each of those rectangles from x equals a to x equals b. All right, and so that's the whole point of this. So when the region R is a geometric shape, we can use the appropriate area formula. For curves, however, you must use the limit of a summation. All right, and we're going to sum all of the areas of each of those little rectangles. So let's have a look at example number 4. It says, use the 5 rectangles in the figure. And oh, by the way, because there's 5 rectangles, n is going to equal, guess what? 5. Okay, so use the 5 rectangles in the figure to approximate the area of the region bounded by the graph of f of x equals 6 minus x squared, the x-axis, and the vertical lines x equals 0 and x equals 2. Now, look at this, this picture very carefully, all right? If you notice, we have 5 rectangles. And those 5 rectangles range from x equals 0 to x equals 2. And so each of the rectangles has a width of 2/5. Think about that, right? We're dividing a length of 2 by 5 parts. So each part is 2/5. All right. Now, how are we actually going to calculate this? All right, well, the first thing that we should do is think about what the intervals are. And you don't have to write these out every time, but the first interval is 0 to 2/5. The second interval is going to be 2/5 to 4/5. The third interval is going to be 4/5 to 6/5. Now, 6/5 is really 1 and 1/5, but we'll just leave it as 6/5 for now because it'll make the math easier. Then 6/5 to 8/5. And finally, 8/5 to 2. All right, which is 10/5 if you think about it. Okay, so those are my intervals here. Now, um, the right end point of each rectangle, and I'll draw the one rectangle up here. All right, but the right side is going to be 2/5 times the value of I, right? If it's the first rectangle, it's 2/5 times 1, or 2/5. If it's the second rectangle, it's 2/5 times 2 times 2, which is 4/5. If it's the third rectangle, it's 2/5 times 3, which is 6/5, and so on and so on. Okay, and so that is the value of the end point for each of the rectangles for I equals 1, 2, 3, 4, and 5. Now, what that means is that the sum of the areas for these rectangles, here's my summation sign, I equals 1 to 5. That's a sloppy 1, but you'll get over it. And so the first term that I'm going to use is the height, and that's going to be the y value. So f of 2/5 I. And then I'm going to multiply that by the width of each rectangle, which is 2/5. Okay. Now, I'm going to set this equal to the sum of I equals 1 to 5. 5. And I know that f of 2I over 5 is going to equal 6 minus 2I over 5. And then I'm going to square that term, right? Because f of x equals 6 minus x squared. Well, the x value is 2I over 5, all right? And then I'm going to multiply that. I'll put this in brackets. I'm going to multiply that by the width, which is simply 2/5. Okay. Now I'm going to use my my skills in summations. First thing I'm going to do is I'm going to pull out the 2/5. All right, because that's a constant, and I can do that. Is the sum of, or is I equals 1 to 5 in this case, and I'm going to break up the other numbers here. I'm going to make this the 6 minus, and then the 2I squared is going to be 4I squared over 5 is going to be 25. So I'm going to pull out the 4/25 and multiply that by I squared. Okay. And dang it. Then this is going to become 2/5, and we're multiplying the 2/5 by the whole kit and caboodle. So it's going to be 2/5 times the sum, and I'm not going to write the I equals 1 to 5 anymore. It's going to be the sum of 6 minus, and this should be in parentheses. Dummy. So 6 minus 4/25 times the summation of I squared. Now, remember what the rules are for this. The This is going to be 2/5 times. Now, the summation of 6 is c times n, the constant. So this is going to be 6 times 5, right? Because this is n. And then times 4/25. And for I squared, excuse me, it's going to be n, or well, 5 times 5 plus 1, all right, because it's n plus 1, times 2 times 5, which is 10, plus 1, all over 6. Okay? Now we do some arithmetic here. This is going to be 2/5. Come on now. 2/5 times 30 minus. Now, 5 plus 1 is 6. 10 plus 1 is 11. 6 times 11 is 66. And 25 times 6 is 150. All right. And so this is going to, come on, this is going to simplify to 44 over 5, I think. I believe so. It's 10 times 7. Yes, 44 over 5. All right. And then 30 times 2 is 60/5. And then 2 times that is 88 over 25. So 5 times 60 is 300, minus 88 is 212. So this is going to be equal to 212 over 25. Now, 25 goes into 200 8 times. So this is going to be a little over 8, almost 8.5. So I'm just going to call it 8.5 and call it a day. All right. And so the approximate area of the region bounded by the graph f of x equals 6 minus x squared between the x-axis and between the vertical lines x equals 0 and x equals 2 is approximately 8.5 units. Okay, so that is example number 4. Now, if you're taking the area of any plane region, meaning flat region on a graph, not 3-dimensional, but just 2-dimensional, and f is a continuous function and non-negative on the interval a comma b, then the area of the region is bounded by the graph, the x-axis, and the vertical lines x equals a and x equals b, and it's given by a equals the limit as n approaches infinity of the sum of I equals 1 to n of f of a plus b minus a times I over n times b minus a over n. Now, for the love of God, all right, where this piece right here represents the height, this is the y-axis, and this part here represents the width. All right, because the rectangle is always height times width. All right. Now the A's and B's are just the values on the x-axis between point A and point B. That's the area that you're trying to do. So it's the total width. But the height is a function of the width. So that's why we have the function notation, f of that mess. All right. Now, what does that mean for us? Well, let's say we try to find the area of a region. So find the area of the region bounded by the graph f of x equals x squared. All right, and you can see that here's the part of the parabola right here. And the x-axis between x equals 0, so right here, and x equals 1. So we'll keep the math as simple as we can in this case. All right. The dimensions of the rectangle are first. So the width here is simply going to be b minus a divided by the number of rectangles that we decide to do. So if we just do two big rectangles, boom, boom, all right, we're going to end up with n equals 2. But if we divided this into 10 rectangles, then each n would, there'd be 10 n's, 10, or n equals 10, and each rectangle would have a tenth as its width. Now, the length, on the other hand, is going to be equal to the value f of a plus the difference b minus a times whatever I value we're talking about, all divided by n. Okay? Now, in this particular case, in this particular problem, because x is between 0 and 1, then the value of b is going to be 1, and the value of a is going to be 0. So this is, the width is going to be 1 minus 0 divided by the number of rectangles I decide to draw. So there's the width, all right, which is obviously just 1 over n. Okay, the length is going to be f of 0, that's the a value, plus 1 minus 0 times I, divided by the value of n, which is I over n. Okay, so f of I over n. All right, and that is going to be I squared, because f of x equals x squared, so it's going to, I over n squared is going to be I squared over n squared. All right, so the next thing that we want to do is we want to calculate the area. Well, the area is going to be equal to the summation from I equals 1 to n of f of a plus b minus a times I over n times, and I'll put this whole kit and caboodle here, b minus a over n. All right. Now, I can simplify this, of course, because this is now going to be the summation. And, oops, too many variables there, too many squiggles. So this is just going to be the summation, and this is going to be f of a plus b minus ai over n is going to be I squared over n squared, and b minus a over n is simply going to be 1 over n. And if I multiply these, it's just going to be the summation of I squared over n cubed. So what do I do here? The first thing I do is I pull out the n cubed, or the 1 over n cubed. So 1 over n cubed times the summation of I squared. All right. And lo and behold, I already know what that is. All right. This then becomes 1 over n cubed times, and this value, of course, is going to be n, come on, times n plus 1 times 2n plus 1 divided by 6. Now, do a quick bit of arithmetic and magical mumbo jumbo, and I end up with 2n cubed plus 3n squared plus n all over 6n cubed. 6n cubed. Divide the n cubed out, and that's going to leave me with 2 plus, 2 over 6 plus 3 over 6n plus 1 over 6n squared. All right. Now remember, if we're taking the limit as x approaches infinity, then in this case I'm left with 2/6 plus 0 plus 0, right? Because if n approaches infinity, then 3 over 6 times infinity is 0. 1 over 6n squared, if n is equal to infinity, is 0. And so the limit here, the area bounded by this, is going to be equivalent to 2/6. And you can obviously reduce that fraction to 1/3 if you want. Okay, so that's example number 5. Let's have a quick look at example number 6. In this case, and I can barely see that. It's a very blurry photo. But find the area of the region bounded by the graph of f of x equals 3x minus x squared, and the x-axis between x equals 1 and x equals 2, as shown in the figure. So this value is going to be my b value. This value is going to be my a value. Here's f of x. And what we need to do is figure out what we want to do for the rest. So the width is, of course, again, going to be b minus a over n. And in this particular case, that's going to be 2 minus 1 over n, or 1 over n. So there's my width value. The height value is going to be f of a plus b minus a times I over n. Okay. And so I want to multiply these, in this case, well, let's do the actual arithmetic here. Come on now. This is going to be f of a is equal to 1 plus b minus is going to be 2 minus 1 times I over n. And this is going to be equal to f of well, actually, we'll just do the 3x minus x squared. And so in this case, it's going to give me now in, all right, I'm just going to quit. I don't know what the hell is going on with this mouse today. All right, let's just go to this slide and try it again. And so the value of the area is going to equal the summation as from I equals 1 to I equals n of, and this becomes 2, because the value of a is 2, and then the other term is going to be b minus a times I, which is 1 times I, or simply I, over n, and then minus I squared over n squared. And then multiply that by 1 over n. All right. Now, what I did here was I actually used f of x equals 3 minus x squared to come up with this, this term. Now, in the first part, I'm going to pull the 1 over n right out. Okay. And then I'm going to do 3 summations. The summation of 2 plus the summation of 1 over n plus the summation of I'm sorry, that's I over n, rather, I lied. Gosh darn it. I over n plus the summation of I squared over n squared. All right. Now, the summation of 2 is going to be 2n. So this is going to be 1 over n times 2n plus 1 over n. Now, the summation of I over n is going to be, pull the 1 over n out, and so it becomes 1 over n squared times the summation of I, of course, is n plus, or I'm sorry, times n plus 1 over 2. And then finally, the summation of this is going to be 1 over n cubed This is a minus sign, by the way. This is a minus sign. Sorry. 1 over n cubed times, the, for I squared over n is going to be n times n plus 1 times 2n plus 1 over 6. Okay? Now, if I then go through this and do a little bit of quick math, this becomes simply 2, right? 1 over n times 2n is 2. Over here, this one, this becomes n times n is n squared plus n divided by n squared. What that's going to leave me is n squared plus n. All right, we'll just distribute that over 2n squared. Okay, and then for the last one, this one is going to be n times n is n squared plus n, and then multiply it by this, and you're going to end up with 2n cubed. Come on now. 2n cubed plus 3n squared plus n. And that's all going to be over 6n cubed. Okay. Now, if you take the limit of these scenarios, well, actually, let's make this even simpler. This is still 2. If I divide both sides here by n squared, I'm going to end up with 1 plus I'm sorry, 1 over 2, right? Plus 1 over 2n. And then over here, 2 times n cubed divided by 6 times n cubed is 2/6 minus 3n squared over 3n cubed is going to be equal to 1. I'm going to reduce the fraction. 3 over 6 is 1 over 2. So 1 over 2n. And then n over 6n cubed is going to be 1 over 6n squared. Okay? All right. So those are all of the terms then. Now, if you do a little bit of arithmetic here and combine like terms, first, all of the terms with an n in the denominator are going to cancel out, because if n approaches infinity, the denominator gets bigger and bigger and bigger, the number gets smaller. And so this becomes 2 plus 1/2 minus 2/6. If you convert everything to sixths, this is 12/6 plus 6/6 minus 2/6. 12 plus 6 is 18, minus 2 is 16. So this becomes 16/6. Whoops. I'm sorry, that's dumb. This is 3/6. 12 plus 3 is 15, minus 2 is 13. All right, and so this becomes 13/6, which is just over 2. Okay, 13/6. All right, so that, my friends, is example number 6. All right, this is a long problem and it looks complex, but if you take it a step at a time and are very careful with your algebra, you should do okay. All right, that brings us to the end. And so your homework assignment for next time is to do the odd numbers at the end of section 12.5, numbers 1 to 45. And I hope that you learned something.